Okay, in this video we're going to look at pH changes in buffer solutions. But the examples that we're going to see here are very similar to the examples that we just did in the previous video. So we know that buffers resist changes to the pH. However, when we do add an acid or a base to a buffer, the pH does change. It changes by a much smaller amount than it would be if we'd added that acid or base to a non-buffered solution, but the pH does still change. However, these calculations are going to be very similar to the ones that we just did. They're going to involve two steps, just like the last ones. First, we'll do a stoichiometry calculation, where we'll be working in moles, and then we'll look and see what do we have left after that stoichiometry reaction, and then that may require us to do an equilibrium calculation, or if we had some strong acid or strong base left over, then it's just calculating the pH of a strong acid or a strong base. So let's go back and use the same solution that we started our discussion of buffers on. So in this case, we have 2 liters of that solution, and we have 0.2 molar acetic acid and 0.1 molar sodium acetate. And so we want to calculate the pH after we've added some number of moles of sodium hydroxide. All right, so the first thing we need to decide is what is the sodium hydroxide, or since it's a strong base, we'll just use hydroxide. What is the hydroxide going to react with? Well, the 2 components of our buffer are acetic acid, and then we have sodium acetate, but again, this is a salt, so I want to get rid of that sodium. What I'm really interested in is the acetate ion, which is the conjugate base of the acetic acid. And so hydroxide, or sodium hydroxide being a base, isn't going to react with the weak base, it's going to react with the weak acid. So the reaction that we have going on when we add the sodium hydroxide to our buffer is that hydroxide is going to react with the acid of the buffer, and these stoichiometry reactions are going to go to completion, and so that's going to make water and acetate ions. And so we need to do a BCA table. And remember, when we do these BCA tables, we've got to be sure that we're working in moles. And so for the hydroxide, they already gave us the moles. We can go ahead and put that in. For the acetic acid and the acetate ions, we need to use the molarity equation to get the moles, right? So M is N over V, or N is M times V. So for the acetic acid, we have 2 molar, or 2 moles per liter, times 2 liters. So we have 0.4 moles of acetic acid, for the acetate ion, we have 0.1 mole per liter, still the buffer volume of 2 liters, so we have 0.2 moles of the acetate. So we'll go ahead and put in the starting moles of acetate are 0.2, the starting moles of acetic acid are 0.4, right? The water is not going to change the pH, so I don't really care about how many moles of that we make. When we do the stoichiometry problems, we have to determine our limiting reagent. So again, we've got a 1-to-1 molar ratio. So the hydroxide is going to run out before the acetic acid. So that will determine the change. And so then after that stoichiometry reaction is finished, we'll have no hydroxide we'll have 0.39 moles of acetic acid. We'll have 0.21 moles of acetate ion. And at this point, I still have a buffer, right? I still have a weak acid present and its conjugate base. There's no strong base left over. So when calculating the pH of a buffer, we can use the Henderson-Hasselbalch equation. So and I'll just give you the pKa. We found that in the previous problem. So the pKa of acetic acid is 4.74. So the pH is going to be 4.74 plus the log. And I made this argument in the last video. Technically, when we use the Henderson-Hasselbalch equation, we should be using concentrations for the base and the acid. However, in this case, both the base and the acid are going to be in a solution that's 2 liters. So I could convert the moles from the BCA table back into concentrations, but in the end, when I divide the base by the acid, the volumes are just going to cancel. And so in this case, it's okay to go ahead and use moles here. Now, if you're ever not sure, formally, we should be using molarities in the Henderson-Hasselbalch equation, but in this case, because the volumes are going to cancel, it's okay to use moles. So I have the base over the acid, so I have 0.21 over 0.39, and so I get a pH of 4.47. And you may not remember, if you go back and look at your notes, before we added anything, right, before I added solid sodium hydroxide, if I just wanted to know the pH of this buffer solution before anything was added, we did that calculation earlier. And so before adding hydroxide, the pH was 4.44. So since we added base, it's not surprising that the pH went up, but it certainly didn't go up very much. And so the buffer effectively resisted the change in pH. It didn't eliminate the change in pH, but it made it much less than it would have been. All right. Now, just to put the previous calculation into context, right, how good are buffers at resisting changes in pH, let's just consider what would have happened if we added that same amount of moles to the same volume, but now of distilled water. So, to do this calculation, right, we'll just take the moles of hydroxide, divide that by the volume to get the concentration, get the pOH, and then the pH. So I'll leave you to do that, but to save time, I'll just give you the result. In this case, if we added the same number of moles as we use of sodium hydroxide as we used in the last problem, and just added it to distilled water, the pH would have been 11.7. Right? And so you can see how effective the buffer was at resisting changes in pH. Right? In this example here, the neutral water, the distilled water, the pH would have been 7. When I add that number of moles of sodium hydroxide, the pH went from 7 to 11.7. Right? So that's a 4.7 pH unit change. When we added it to the buffer, it was only a 0.03 pH unit change. So that buffer was very effective at resisting what would have been a large change in pH. Okay, here's another example. So first we're asked to calculate the pH of a 1.0 liter solution that is 0.04 molar in nitrous acid and 0.025 molar in magnesium nitrite. So this is a buffer. I have a weak acid, and this salt is going to dissociate to give me nitrite ions, and NO2 minus is the conjugate base of HNO2. So I have a buffer. And so we can use the Henderson-Hasselbalch equation to calculate the pH of a buffer. We just have to be a little bit careful, right? When this magnesium nitrite dissolves in water, what's going to happen when this salt dissociates, for every 1 mole of magnesium nitrite we have, that's going to produce 2 moles of the nitrite ions. So if the concentration of magnesium nitrite is 0.025, the concentration of the nitrite ions is going to be 2 times that. So the concentration of NO2 minus is going to be 0.025 times 2. So the concentration of my nitrite ions is 0.05 molar, not 0.025 molar. Okay, so to get the pH of a buffer, I'll use the Henderson-Hasselbalch equation. I need the pKa, so the pKa is the negative log of the Ka. So for the pKa, I have 3.34. So then my pH the concentration of the base we said was 0.05. The concentration of the acid is 0.04. And so for the pH I get, let's do that a little bit better, 3.43. All right, so that was the answer to the first part of the question. Just what is the pH of the buffer before I added anything to it? All right, the next part of the problem is what is the pH after I add 0.02 moles of HBr? So we'll do the bulk of this on the next slide, but before we go to the next slide, let's decide what is the HBr going to react with. So HBr is a strong acid, right? And so we can either react with the HNO2 or the NO2 minus. Well, HNO2 is a weak acid, so an acid is not going to react with an acid, but the NO2 minus is a weak base. So the strong acid will react with the weak base. So we'll start on the next slide by writing the chemical equation for that reaction. Okay, so we said the strong acid is going to react with the NO2 minus, so let's go ahead and write that chemical equation. So because HBr is a strong acid, I'm not going to write HBr, I'm going to write H3O plus is going to react with the weak base, NO2 minus. This reaction will go to completion, so we'll have water plus HNO2. Alright, so we start with the stoichiometry problem. So I need to know the moles. They just gave us the moles of the strong acid, so I can put that in. And I'm going to skip the moles calculation because it's pretty easy. Right, if I have a 1 molar solution and I have 0.04 moles per liter, 0.04 times 1, I'm going to have, nope, wrong place, 0.04 moles of the nitrous acid. Remember that we said the actual concentration of nitrite is 2 times this, so I have 0.05 molar nitrite, but with a 1 liter solution, 0.05 times 1. Again, remember, these are all in moles. So I have 0.05 moles of NO2 minus. The water, we can ignore, it's not going to affect the pH. So the limiting reagent between H3O plus and NO2 minus is the H3O plus, so that determines the change. Alright, so when that reaction finishes, I'll be left with no hydronium ions. I'll have 0.03 nitrite ions, and I'll have 0.06 moles of nitrous acid. And so if I'd had any H3O plus left, I'd have used that to determine the pH, just by determining the pH of a strong acid. But I don't have any of it left. I have a weak base in its conjugate acid, or a weak acid and its conjugate base, however you want to think about it. So I have a buffer, so I can use the Henderson-Hasselbalch equation. Again, normally in the Henderson-Hasselbalch equation, we would use molarity, but by the time I've divided those both by the volume, those are going to cancel. So it's okay to go ahead and use moles in this instance. So the pH we found the pKa on the previous slide. The base is 0.03. The acid is 0.06. And so I get for the final pH 3.04. All right, and we saw that the original pH was 3.43. And so we did effectively resist the change of the pH. It was a greater change than in our first example, but we're using less volume and lower concentrations of our buffer, and we added more acid, so I think we would have expected a larger change than the change we saw in the first example.